Hi, my name is Chiara Bruzzi, and I'm going to be showing you my research updates up to this point. So to start off with a little bit of an introduction of my project, I'm looking to investigate the characteristics of the magnetization plateaus in the anisotropic Heisenberg model on a Kagome strip chain at 0 Kelvin. This is a frustrated system, which as you can see from the figures, that means that not all of the electron spins are balanced out, so it can't reach the lowest energy level. For non-frustrated systems, the magnetization curve has an exponential increase until it reaches the saturation magnetization. For frustrated systems, as you decrease the value of the magnetization from saturation, you encounter plateaus. The stability, nature, and origin of these magnetization plateaus is the interest of this project. What is the motivation of the project? So this project is mainly motivated by previous studies of magnetization plateaus, and they want to better understand the anisotropic effects and inhomogeneity of frustrated systems. I'm mainly going to be looking at the stability of magnetization plateaus previously observed at a level of a value of 0.2 and 0.6, as well as the existence of possible plateaus at 0, 0.2, 0.4, and 0.8. Lastly, I'm going to be looking at the magnetic structure and nature of the plateaus. To carry out this experiment, it can't be done in a laboratory because it's done at 0 Kelvin. So we will be using a numerical algorithm, the density matrix renormalization group, DMRG. This is a non-perturbation numerical method that offers high accuracy in approximating the ground state wave function for large systems in low dimensions. So to start off the project, I looked at the anisotropic spin chain, which was just an example model. The Hamiltonian that was used is here. This is the formula, and this is just showing where the class parameters come for the code, and the class parameters are used to mimic the behavior of the structure. So from these results, I was able to get the SX values, which are the on-site expectation values for two different sites. So that means two different unit cells. And these results matched my mentors, which was good. And that meant that I could move on because the simulations were running correctly. So next I looked at the Kagome strip chain and the Hamiltonian here. As you can see, it has a little bit more components than the previous example. So the interaction strength is in three different directions: JH, JU, and JD. JH is for the horizontal bond, so that would be between 2 and 5 and 1 and 4 in this figure on the bottom right. JU is for the upper two green bonds, so 2 to 3 and 5 to 3. And JD is for 1 to 3 and 4 to 3. Also, it has a delta component, which is the anisotropy of the Heisenberg interactions. The boundary conditions are kept to infinite, which means an infinitely long chain. This figure here represents the structure of the Kagome lattice, and it has 5 sites in each unit cell. So this figure is representing 2 different unit cells. So for the results, I was able to get results that matched those found in literature, where there's a magnetization plateau at 0.2 and 0.6 by tuning the magnetic field strength by 0.1 between 0 to 3. That was also a good result, and that meant that I could go to my next step of looking for new possible plateaus. So in doing that, I varied the magnetic field strength by 0.01, and from a general look at the results in this region of 0 to 0.5, I was able to find that maybe there was a possible plateau at a magnetic field strength of 0. I isolated that and found that between 0 and 0.02, the magnetization was actually significantly different. So maybe the plateau didn't extend until 0.02, but between 0, 0.05, 0.01, and 0.015, the magnetization values were all within the error limit, which meant that they could actually be all the same, and that could actually be a possible plateau. So what are my next steps? For my next steps, I'm looking to reproduce the results with L is equal to 1 and L is equal to 3. So that means 1 unit cell and 3 unit cells. I'm also looking to examine plateaus at a magnetization value of 0.4 and 0.8. Investigate the anisotropic and inhomogeneous effects of those plateaus, and reproduce figure 2.B and 2.C that you can see here, which look to analyze the spin correlation at the observed plateaus. Thank you for your time, and I hope to get back to you with more updates soon.